Thank you, Greg. So I said before, the topic of this presentation is time of flight, in particular some basic facts about time of flight. So I will start with the definition. So with this time of flight is the measure of the time of photons traveling at the speed of light from a point A to point B. And so everybody knows what photons and speed of light is, but I want to go through some basic facts about photons and speed of light, especially what they imply for our system. So photons are, of course, particle lights, and as we know, the electromagnetic spectrum is really wide. So what we see is the word in between. So in the middle of this band, and is the visible. But our system doesn't work in the visible. Works a bit on the left side of the visible at 940 nanometers. And it's compared to the wide range of spectrum, is really close to the visible range, but it's not quite, because our human eye cannot really see it. And so without photons, the photons are particles, and the particles of light, and they travel at the speed of light, and that is the max speed of the universe. They carry energy, and they are never alone. That means since they are a particular kind of particle called bosons, they try to stick together. So and essentially you see them all in a big number, a huge number. To give you an example of how big this number is, you can look at this small calculation. So assuming that our wavelength, the wavelength of our system, of our sensor, is 9040 nanometers, and you have 100 milliwatts for a pulse of a duration of 50 microwatts. If you know the energy of the photon and the energy of the total energy emitted in a pulse, you just divide the two, you can get the number of photons in a pulse. And that's, as you can see, it's a huge number. It's 24,000 billion photons just in one pulse. So that's a really, really big number. And as I said, they travel at the speed of light. So they travel at the fastest speed you can imagine, and more, maybe you can imagine faster, but this the fastest you can have in the universe. And so to get an idea how fast they are, they can travel from the sun to the earth in only 8 minutes, from the earth to the moon in 1.20 seconds, from the Mont Blanc, that is close to us, 80 kilometers from here. It's they do this in 0.00026 seconds. And the other distances, other times. But just to give an idea, the rule of thumb for us, for a sensor system, is they normally they travel in one nanosecond. They travel 30 centimeters. So back to the time of flight. We have a sensor, that is our device. We have a target that is on the right, and what you want to know is the distance between your sensor and your target. What we said, that actually what you measure is the time that the photons take to go from your target, from your sensor to your target, and then back. So if you want to know the distance, that's easy. You know the speed of light, there's a constant, at least in air, and then you divide it by 2, because actually what you measure, the time you measure, is the time for the photons to go to the target and back. But you're only interested in half of this, so the distance. And so that's what we need to measure this time to get the distance. The three main ingredients, as you already know, are the sensor, the target, whatever you want to measure, an object, a surface, a wall, and the environment. The environment is whatever is in between your sensor and your target. But let's start with the target. And So the target is there are many kind of targets. So depending on the type of surface you have. For example, you can have a mirror that is specular. So it means that you enter with a direction and you get off with the same direction but in opposite. So with the same angle but in opposite direction. And you can have diffuse that is actually you enter with a certain direction but you get out with an isotropic emission, so in all directions. And you can also have something in between. And so, for example, so something between, so a combination of specular and a diffuse. And at the same time, the target. So this is how the light is reflected back. So the way the light is reflected back. But it's what is important is also the intensity of the light that is reflected back. So the what we just call reflectivity. You can have materials that actually reflect back all the light that hits the surface itself, and you can have materials that actually, like this black car, that actually reflect back only a small percentage of the light that gets to them. And of course, you have also to be careful because when we talk about reflectivity, normally, well, when you talk about reflectivity, you talk about visible light, so what you can see. But actually, the reflectivity has a dependence on the wavelength. So maybe something is really reflective at the wavelength that you can see in the red, for example, but it's not so reflective at 940. There is the wavelength of your sensor, and or the other way around. So this is a point that should be taken into account. And the target also it's not always as smooth as regular as you may think. So, for example, your sensor send all these photons. Let's focus on two of them. So the A and then the B. The A takes this path, and the B takes another path that is slightly different. So when your photons actually calculate the distance, it takes a kind of average of all the photons that go back, and those photons they might have traveled slightly different distances. And this is, but okay, normally for a wall, for a surface that is fairly smooth, this distance from this of time and then distance is not so big. A problem might arise when actually you have some walls, for example, that are really close to the optical axis of your system. So you have still your photon A, your photon B. They travel a slightly different distance, but not so huge difference. But let's say you have another photon that before arriving to your target gets to a surface that is parallel to your optical axis. But still, the C distance is much bigger than both A and B. So when your sensor actually calculate the total distance, it doesn't care that C and A and B are different. You just make an average of all this, and then the average could be different because C has a different weight. It's a different distance. So the distance you actually measure is not the real one. It's affected by these faults, if you wanna call like that, measurement that they are due to this bouncing in some walls close to your optical axis. And this it has an effect that is actually pretty known. It's called multipath effect. So the way that your light propagates from your sensor is different than our sensor, the source light source of our sensor are LED, and in some of them they are pixels. So they are sources. They are not like a laser. So the laser is a source that is quasi not divergent. So you get out with an angle or with a width, and this width stay constant for a long time. In the case of LEDs, it's so at the exit is almost point, but then it spreads out. So there is it diverges, and so the area that it covers, it's really dependent on the distance you are from. So if you are really close, the area covered by your LED is small, and then of course if you are really far away, this area is much bigger. And this is important because this is no. If in this other slide you can see that if you try to calculate how much of the photons are coming back, depending on how far you are from the sensor is far from your target, and also take into account the reflectivity of the target, you can get some really different numbers. For example, look at these three examples. You have a EVO 60 meters is one of our sensors that measure until 60 meters. And the target distance of this is at 10 meters, for example. You have a target that is completely 100% reflected, and so under reflective, and then at 1 meter, at 10 meters, you illuminate 80 times 80 square centimeter. And the EVO lens is 1 centimeter. So if you divide your surface divided by the area you illuminate, you get the only 0.016% of the photons come back to the sensor. This number goes pretty fast down. If you actually, instead of having 100% reflective mirror, you have a 80%, but this time conversion surface. So a surface that is not specular. And so this number goes down pretty much, and it's about 100%. So you have to divide the number before by 100, and then you get something like 0.0014%. The same thing. So now we consider the same target at 88%, and the target distance instead of 10 meters is 60 meters. Now, as you can see, since your target is much farther away, it's 60 meters instead of 10 meters. These numbers is dramatically going down, and actually doesn't go down. So it goes down, and you have like 0 followed by 6,039. So this is a really small number respect to the percentage respect to the number you actually send out. And but still, even though this percentage might look really low, you still have to remember that the first number we introduced, so the number of photons you actually send per pulse, that's 24,000 billion per pulse. So that this small percentage is still a huge number, and compared to get a reasonable decimal quantity of photons in order to make your measure. So as I said before, the ingredients that you need for your measurement, the sensor, the target, and the environment. What's the environment? The environment. So let's imagine you want to measure outside, and there's a sunny day, and there is of course a lot of light. Normally, time of flight sensor are really sensitive to ambient light. And if you look at the spectrum of the sun on the spectrum on the left side, you can see that the sun has a huge spectrum in the sense of the range of the wavelength is really large. It goes from 250 to 2,500, especially at the sea level. So the red curve, you see that there are actually some zones where the radiation seems to be lower. And for example, at 940, a bit farther at 1100, at 1400, and so that's why you actually, in our case, the source we chose is 940. As you can see, at 940, there is a dip in the emission of the radiation from the sun, or at least there is a dip in what do you of the detected radiation from the sun. So you can use the dip to actually try not to have an interference, so an interference of the sun on your sensor. And then so you that's why I actually use 9.4. Still, you have to be careful because if you are on a really bright day, a sunny day outside, this number, even though it's much lower than other wavelength for the radiation, is still a huge number because the sun is really powerful. So this is something that you should be taken into account when you try to measure the distances with our sensor, but actually with any time of flight sensors in bright conditions. Another so the sun could be a problem, but there is also some other conditions that could be detrimental for your measurements, and that's for example when you have heavy rain or fog, and that means that in between your sensor and your target there are particles of water vapor, and this water, as for the multipath effect, can have some effect on the measurement of your distance. This is because your photons mostly they arrive to the target, but many of them, instead of before arriving to the target and back to your sensor, they actually either reflected by one of these particles, and then they go in direction that actually are not usable anymore because they are not detected, or they go to particles that are really close to your sensor. So the distance that these photons travels is much lower than the distance of the target. And so they enter in your average and they give you a distance that is not the one you want. This is actually, it's not an effect that it's really important. That, let's say, if you are not in extreme conditions, if it is a really heavy rain or really foggy, then it might be important. But if you're in normal conditions, not much fog and light rain, this effect is not so huge as you might imagine. So this brings actually to the end of my presentation. I want to share some new topics, next topics for future webinar, and actually, if you can also propose more if you want. But these are some that actually we thought about. So we know that the time of flight can be direct and indirect, and so would be useful for people to know what's the difference between a direct time of flight and indirect time of flight. In our case, the most of our sensors are indirect time of flight, so would be useful to talk a bit, into more details about the indirect time of flight. So what's the idea behind? What is a phase? The phase is what you measure in an indirect time of flight. The range ambiguity, how to measure actually the phase, and then the principle of superposition for different phases. And actually, what are the advantages of disadvantages of the indirect time of flight, if you compare to other technologies, for example, the direct. And another one of the topics that actually could be interesting also, it's the so-called crosstalk, and that it's an effect that you have if you cover your sensor with a cover glass, or if you have two sensors that actually work really close to each other. And with this, I would like to thank you for your attention. And if you have questions, please go ahead. Thank you.
Hi, Salvo. Thanks very much for that. Greg speaking again. Yeah, we've had a number of questions, actually. I'm sure we won't have time to go through all of them if we respect the half-hour timing. But I'll try to pick a few out, which I think will be kind of generically interesting to everybody on the call. So you were talking a minute ago about the sun and 940 nanometers. And so one of the questions here is, does this mean that most environmental infrared radiation at 940 nanometer comes from the sun, are there any other natural sources that we should consider?
No, for 940, the main natural source is the sun, and but this is actually, yeah, it's only the sun, but this is actually important. It takes really, it enters in your calculation, in your measurement, at really bright conditions. Also, for example, today here in Geneva, it's not so sunny, so it's pretty cloudy. In these conditions, actually, the influence of the 940 is not so big, so you could actually measure reliable outside. Um, yeah.
Yeah. That leads on to a question that I get asked very commonly at trade shows and that kind of thing, which is that can these sensors work outdoors? And the short answer is yes, they can. And the slightly longer answer is high levels of sunlight will affect the performance. So our Evo 60-meter sensor, for example, that can achieve a 60-meter range in indoor conditions. If you take it outdoors on a very bright sunny day, you are going to see reduced performance, and it's typically the range that suffers. And then other factors come into it as well, such as the reflectivity of the target that the sensor is pointing at. So a white wall, for example, is a good target and will return more photons than grass and perhaps asphalt. I think one of the worst surfaces we ever saw was a rubber running track, which absorbed lots of photons and simply meant that the sensor received less less signal back, and therefore that impedes the performance. Let me pick up another question here before we draw to a conclusion. I think we perhaps covered this, but David asked, do you need to point the sensor straight at a target, or can you be at any angle? And I think you perhaps spoke a bit about this, Salvo, with the multipath effect.
Yeah, I mean, the best would be to go straight to the target, even though even a slight angle can be acceptable. Of course, if you are at an angle that is really high or really small, depends how you look at it. So if you are at a grazing angle respect to the target, of course you're gonna not. There's not much return. Also because the light will be bouncing back on the other direction respect to your sensor. So I would stay as much possible as frontal to your target, if possible.
Yeah, very good. Maybe time for one last question. Let me see, what do we have here? This one was quite academic, actually, and I don't know the answer, which is why I'm quite curious to pose it. So if I summarize the question, I understand it as this. The absolute speed of light is that measurement usually taken in a vacuum, and is the speed of light slower with if it needs to travel through the atmosphere or water?
Yeah, it is, because the speed of light depends on the medium. But so the speed of light, it's an absolute number in the vacuum. But of course, if you are traveling in a medium, it's lower. But this doesn't. It's not. I mean, it's not important for our system, because the speed of light, even in air, it's almost as the one in the vacuum. It's not much slower, so it doesn't. It's not an important factor. No, the speed of light in our system is 300,000 kilometer per second. So it doesn't.
Okay.
It can be considered constant. Let's say this.
Okay, I think that
understand the question. I think the question.
Yeah, I think that answers it. So one final and very quick and easy product-related question, which came quite early on. The slide I showed had 3D Cam, our 80 by 60 pixel 3D camera, straddling the line between OEM design in and industrial. And the question was, why is that the case? And the simple answer is that it comes in a robust aluminium housing, and by definition of that, it has a degree of ruggedness, but it has a USB interface, which we don't consider to be, industrial grade. So that's why it sits between the two. I think in view of time, we will stop there with the questions and answers. I hope everybody's found this useful. We really appreciate your feedback. And as Salvo said, we're very happy to do more webinars. This is the first live one we've done. So if you have specific things that you would like us to talk about in future webinars, we'd like to hear that. We have recorded today's session. Provided that the recording is successful, we will circulate that to you. And clearly, if you have any questions about today's content, or you have a need for sensors and an expertise around sensing, please do contact us. We're available to you, and we're very happy to help. So with that, thanks very much, everybody, for joining, and we look forward to welcoming you to the next webinar.
Thanks. See you next time. Bye-bye.